In our last episode, we delved into the kinetic molecular theory. We saw how molecules behave in solids, liquids, and gases. Today, we will take a closer look at the solid and liquid phases of matter. We will also discuss the basic types of solids, surface tension, and humidity. Here are a few samples of solids. Can we classify them into basic types, just as we classified matter into mixtures and substances? Yes, we can. We can group them into two basic types. The first group are the crystalline solids. Just like these models of crystalline substances, sodium chloride, iodine, iron, and silicon dioxide. The basic building block of the lattice is a unit cell. The unit cells, stacked together in an orderly pattern, build up to form the crystal. We can group the other remaining samples of solids into a second type called amorphous solids. This time, the particles are arranged in a random manner. Because of this, they usually appear powdery, dull, or opaque. Most amorphous solids, like glass and plastics, are made up of long chains of atoms and big molecules that do not stack up well. These substances solidify before their molecules can form neatly arranged structures. Here are two solids made up of the same substance: quartz, a mineral, and glass, usually a man-made material. Both of them are made of silicon dioxide or silica, but quartz is crystalline while glass is amorphous. Given enough time, the particles of quartz form an orderly pattern under the earth. When silica melts and hardens, it forms a glass. The atoms of this glass make up a disordered network. How else do we distinguish between crystalline and amorphous solids? The melting point of a crystalline solid like picric acid can be determined using this setup. Picric acid melts sharply at 122 degrees Celsius. What about an amorphous solid like butter? It melts gradually over several degrees range of temperature. Why do these two types of solids melt differently? This has to do with the orderly arrangement of molecules in picric acid and the disordered arrangement of molecules in butter. To help us understand how crystals develop, Arceli da Silva will prepare a crystalline solid with very simple equipment. First, she will prepare a supersaturated solution of nickel sulfate. Start by heating the solvent to 70 degrees Celsius. She adds solute until no more will dissolve. At this temperature, the solution is saturated with the solute. The solution contains the maximum amount of solute that can dissolve in water at that temperature. Generally, a given solvent can dissolve more solute at a higher temperature than at a lower temperature. Watch as the solution cools slowly, undisturbed. The solution has more solute than the solvent can normally dissolve at a lower temperature. The solution is said to be supersaturated. As our cell lead introduces a small crystal of nickel sulfate, the crystal acts like a seed or nucleus for more crystallization. On and around this crystal, the excess solute in the solution starts to deposit or crystallize. In a few days, we should see a larger crystal. This is the same principle applied in producing artificial rain. Nimbus clouds are seeded with silver iodide crystals. Water crystals form on these seeds, later becoming heavy enough to fall as rain. In a past episode, we discussed how molecules in the liquid phase of a substance have greater kinetic energy than molecules in the solid phase. Molecules of a liquid move past each other and collide with one another. They also attract each other enough to keep them together in a continuous phase. Let's explore this movement in molecules of liquids through a simple experiment. I place a drop of dye in a beaker containing water. Watch how the dye spreads out or diffuses in the water even without stirring. Let's drop the dye into different beakers containing methyl